Hello, and now I want to describe you the difference of the Eulerian and the Lagrangian system. Um, in fluid dynamics, you have different principles to describe fluid flow problems. And one big important principle is the Eulerian principle, and the other is the Lagrangian principle. So there was always this, let's call it, fight between the two theories. Here we see Mr. Leonhard Euler. He lived from 1707 to 1783, and he developed a theory where he divided the fluid into small, let's say small particles or small boxes, and like in a coordinate system, he divided the fluid and he described the fluid flow like on a checkerboard from one cell to the next cell. So maybe like an old computer game. And the other important theory was formulated by Joseph Louis Lagrange. He lived from 1736 to 1813, and he described fluid flow problems more particle based. So maybe if you have a spray and you have single droplets, you can describe the droplets in a really efficient way if you only describe the position of the midpoint of the droplets. So here you see a description of the so-called Eulerian coordinate systems, and if you want to define a fluid flow problem and if you want to do computational fluid dynamics, first you have to think about which program I want to use and which program how you want to formulate your problem. For example, if you have fluid flow in a river or fluid flow in a big lake, the Eulerian formulation is really convenient. But if you have more particle-based formulation, you have to take the Lagrangian particle system. So here you see the Eulerian formulation. You have a fluid phase like air, fuel, oil, and you divide the whole domain into a mesh like a checkerboard, and then you can describe the balance for every cell. You can describe how much fluid enters the cell, how much fluid exits the cells, and then you can describe the Eulerian law for this. If you have a Lagrangian particle description here, this is better for maybe for coal or ash or droplets for small particles, because you will describe only the position of the particle or maybe the radius of the particle. And here you see what makes this description sometimes a bit difficult. If we come back to the computers, if we have an Eulerian system, the cache of the problem, if you compile your code and you use cache of your computer, every address is totally defined because you have a mesh where the position of the cells never change. They can change, but let's come to this point later. If you have a Lagrangian system for droplets and you need some addresses for the cache on the computer, and if you imagine some problems merge together, or some droplets are divided, then you get additionally need or demand for memory, and this is always not so good if this happens during the run of a program. Okay, so Lagrangian is a bit more sophisticated, and there's always this conflict between Eulerian description of phases, of example of air, flue gas or oil, or if you have a particle phase like coal, ash or droplets, Lagrangian description is much more convenient. But There are many cases where you can combine both methods together, and you can first describe one phases with an Eulerian description and one phases with a Lagrangian description. So that can be also the combination of both methods in one code. So Eulerian description of Eulerian and Lagrangian. So Eulerian description is place-based, so we only have coordinates depending on x, y, z, or maybe the time. And Lagrangian description is particle-based, so you have to store every particle and you have to store every position of particles, and of course these coordinates will change. So if the position of the particle change and the time step changes, you will have a change of these coordinates. Okay, here again we have a picture of this. We can have steady coordinate systems here, where the cells never change during the run, and this is really convenient if you make a computer simulation and all the cells that are in the memory stored will never change their position and never change. Or you can have so-called mobile coordinate systems, Lagrangian descriptions, where you describe the position of every particle. And this will be much more time consuming for the computers, because you have to calculate every coordinate for every particle in every time step. Okay, here's an example of a Lagrangian model. For example, if you have a velocity, you have the derivation, you need the coordinates, and you can have three different types of velocities for the three coordinates in every direction of every axis. For example, here 2 meters in x meters per second in x direction and 0 meters per second in y and z direction. Okay, here you see again the formulation. You have the definition of every coordinate, and every coordinate, every position will depend on a starting position and on a time step. Then you have to store for every time step the new position, and you have to make derivation of this velocity components. You see some results. I made these results for a direct injection gas valve for General Motors, and you can see the plums of the sprays, and there are a lot of 100,000 of different particles, and so you can describe the injection of the different spray plums into the engine, and you can describe if the spray hits the wall of the cylinder or if it hits the spark plug, and you can really plan the distribution of every spray plum inside the cylinder. And here I colored every spray plum, I took a special color for every particle depending on the hole where you inject the particle. You can see, for example, red particles come out of one hole and green particles come out of one hole and orange, and after a while they mix, and then you see the mixing of this spray distribution. Here you can see it, and that's also a point. If you use the Lagrangian model, it's really good for spray or for particle flows or for cold particle flows or injection of some fuels. And if you want to visualize the results, you always have to present movies. You can make pictures and present it in different time steps, but it is really convenient to create movies from the different time steps and present these movies, to give an impression about the fluid flow behavior. Here again you see that's an example. You see the manifold of a cylinder of a piston engine, and you can describe the injection. Okay, where do we use Eulerian methods? Eulerian methods are better for if you describe, for example, flow in a pipe or flow in an armature, and you have a continuum. Continuum. You have, for example, a lake or a river that is filled with water, and you want to describe the movement of the different velocities in this lake or in this river. Okay, here you see the description of Euler's law of motion, and more or less in this lecture we will use Eulerian formulations, and also for our simulation examples we want to use Eulerian simulations. And if you make a formulation of Eulerian movement, you need a time-dependent variable, you need a variable for a term for the convection, where you make the derivation of the momentum of different velocities in every direction, and you need a diffusive term and some source terms, maybe based on gravity. This formulation looks really much like a law you learned in the lecture before, like the Bernoulli's law or Torricelli's law, and it is the Eulerian formulation. It's more or less a formulation of Bernoulli's law in many different directions, for example in 3 or 2 directions.